The second law of thermodynamics states that for a spontaneous process, the entropy change of the universe is greater than 0. But it's so hard to assess the entropy change of the surroundings that it's nearly impossible to calculate the entropy change of the universe. We need a criterion that can be just applied to the system. So consider a spontaneous process limited to only pressure volume work. This process is accompanied by a heat effect, which is equal to delta H for the system. Now the heat effect for the surroundings is negative of that for the system. So if we go back to the second law, delta S of the universe equals delta S of the system plus delta S of surroundings, substituting in for delta S of the surroundings, and we can rearrange that equation till we get something that looks like this. Now this equation can serve our basic criterion for spontaneous change, but we're going to introduce a new thermodynamic property, Gibbs free energy. Gibbs free energy is delta G, which is equal to delta H minus T delta S. So in order to calculate Gibbs free energy, we need to know the enthalpy, delta H, and the entropy, delta S. A spontaneous process will have a delta G value less than 0. So if delta G is negative, it's a spontaneous process. There are 4 possible cases going back to this equation right here. You do not have to memorize these 4 cases. Here's the deal. If delta H is negative and delta S is positive, I'm looking at case number 1, that means delta G will always be negative in case number 1 because H is negative, S is positive, but this quantity back here will be negative. Delta G will always be negative, so in case 1, it will always be spontaneous. Case number 2, if we're using the same equation, delta H is negative and delta S is negative, well, this quantity back here is going to be positive. And so the value for delta G will depend on temperature. Delta G will be negative at low temperature, and it will be positive at high temperature. That's case number 2. And you could do the same equation and apply that to cases 3 and 4 as well. So don't necessarily memorize those 4 cases. Just be able to plug in the values of H and S into this equation right here. So let's look at this problem. Is this reaction favored at high or low temperatures? Well, delta H is positive. Tells me in the problem. Delta S is entropy change. I'm going from 1 mole of H2 to 2 moles of hydrogen. And so the entropy is positive. It's becoming more disordered. And so H is positive, S is positive, so the sign of G is going to depend on temperature. G will be negative, spontaneous, at high temperatures. And this is case number 3. So delta G will be negative if I have a large value for temperature. Free energies depend on their state, and we need to establish standard state conditions. Well, for the most part, standard state conditions are measured at 1 atmosphere pressure, but for a solute, it's 1 molar concentration for the solution. The free energy change when everything is in their standard states is referred to as the standard free energy change, and we get a superscript to indicate that everything's in their standard states. For a reaction in which a compound is formed from its elements, delta G of the reaction is referred to as the standard free energy of formation, delta GF. And by convention, elements have a standard free energy of formation of 0, just like we did with enthalpy, delta H's. So let's look at a couple problems. I'm given the standard molar enthalpy of formation for silver oxide. So I'm told that delta H of formation is negative 30.59 kilojoules for the formation of silver oxide, which means 2 silver plus 1/2 O2. So that's the equation for which I've given delta H. I want to find delta G for this reaction. Well, delta G is H minus TS. Well, delta H for the reaction up here has to be calculated from the delta H of formation that I'm given here. Basically, to go from this reaction to this reaction up here, I have to flip it around and multiply by 2. When I flip it around, it becomes positive 30.59, and then multiply by 2. Minus T, 298, and then delta S for the reaction is 0.13 kilojoules per Kelvin. And so delta G for this reaction comes out to positive 22.44 kilojoules. And what that tells me is this reaction is non-spontaneous because it's positive. So the reaction as written is non-spontaneous. If I flip it around to where silver and oxygen become reactants, it would be spontaneous because the reverse reaction is spontaneous. Let's look at another one here. Calculate delta G for this reaction, and we're given the delta G's of formation for CO2 and for carbon monoxide. Delta G, the reaction, is equal to the sum of the delta G's of the products minus the sum of delta G's of the reactants. We use this for enthalpy. We can use it here for Gibbs free energy. So for the products, we're going to take 2 times the delta G of CO minus delta G of carbon plus the delta G of formation for CO2. Plug in our numbers. That's 2 times negative 137.28. For carbon, I wasn't given the delta G of formation, but elements are given a value of 0. They are always assigned a value of 0, plus delta G for CO2, which is negative 394.38. Keep track of your signs, your positives and negatives. Delta G for the reaction, positive 119.82 kilojoules. And again, it's positive. That tells me the reaction is non-spontaneous as written. So delta G, Gibbs free energy, tells me whether a reaction is spontaneous or not. It has nothing to do with the rate of reaction. So it does not tell me if a reaction proceeds quickly or slowly. It simply tells me whether the reaction is spontaneous or it's non-spontaneous.